That's dealt with the atomic electrons, but what about the nucleus of protons and neutrons? What happens there?
Now, the protons and neutrons are confined to the tiny, dense core of the atom, known as the nucleus. Now, we haven't shown it here because to show it the size of a pinhead, we'd have had to have shown the atom the size of Wembley Stadium. Now, the electrons in the atom are confined by the electrostatic force, but the protons and neutrons are confined by the so-called strong force. So all the particles in the atom are confined, and according to quantum theory, they should all have energy levels. But notice, the electrons have all this room in which to move, but the neutrons and protons are confined to a tiny volume. And the consequence of this is that the nuclear energy levels are very much more widely spaced than the energy levels of the electrons. Whereas the energy levels of the electrons are measured in electron volts, we normally measure the energy levels of nuclei in millions of electron volts. Now, how can we measure these spacings between these nuclear energy levels? Well, one way of doing this is to use Barry's hammer and gong principle. We have to bang, or rather excite, our gong, that's in this case the nucleus, with a very energetic particle. And when it de-excites, a photon is emitted. Now, the energy of the photon will be equal to the spacings between the relevant nuclear energy levels. So we have to measure the energy of that photon to find the exact spacing. Now, remember, the photon will have an energy of millions of electron volts, and in this case, we call the photon a gamma ray. Now, to find out more about this, we went to see an experiment done at the University of Liverpool, done by a group of physicists led by Peter Twin.
In this laboratory, I lead a team carrying out research into nuclear structure physics. From our study of the structure of light nuclei, we became particularly interested in the nucleus magnesium-26. We decided to study the structure of this nucleus by investigating its energy levels. We spent several months planning and preparing the equipment for the experiment. We took a very pure sample of the material magnesium-26, made it into a very thin foil, which became the target, and bombarded it with high-energy alpha particles from the Van de Graaff accelerator.
This entire accelerator provides the high-energy alpha particles, the hammer for our nuclear collision experiment. At the moment, a routine inspection is being made of the main chamber. Here, an enormous voltage will be generated along the tube, and these big rings help control that voltage. The alpha particles emerge from the accelerator with sufficient energies to excite atomic nuclei. The particles travel along this tube, which is evacuated to prevent the particles being scattered by air molecules. A large magnet bends the beam of alpha particles through a thick wall into the experimental hall, where the gong of our experiment, the magnesium-26 target, is brought to the target chamber. Collisions between alpha particles and magnesium-26 nuclei are detected electronically. The signals pass to the computer room for processing and analysis. In terms of the gong analogy, this is equivalent to analyzing the sound waves. Well, that's the experimental setup. Now let's look at it in more detail, starting with the very heart of the experiment, the thin foil of magnesium-26. The first job is to mount it so that it will become a target placed directly in the path of the beam of alpha particles, so that when the accelerator is switched on, the particles will zip through this hole and strike the target. But what happens then?
The accelerated alpha particles are travelling at about 1/10 of the speed of light when they enter the target chamber. Most of them go straight through the target, but some are captured by magnesium nuclei, which are then excited. The captured alpha particle emerges, and then, only 10 to the minus 15 seconds later, gamma rays are ejected. That happens when the protons and neutrons in the nucleus lose their excess energy. So to find the nuclear energy levels, we need to measure the energy of the ejected gamma rays and also the energy of the associated alpha particles.
This is part of the alpha particle detector assembly. The vital component is a thin silicon slice, which gives a pulse of electrical current when an alpha particle hits it. It's placed close to the target, so as to intercept some of the alpha particles scattered from the magnesium-26 nuclei. But alpha particles also collide with air molecules, so the target chamber, like the whole beam path, has to be enclosed and the air pumped out. Gamma rays, however, pass easily through that cover, so the gamma ray detector can be outside. The big tank is full of very cold liquid nitrogen, essential because the detector can only work at very low temperatures. It's a large chunk of specially prepared germanium. Gamma rays don't get through that. They are absorbed and give rise to an electrical signal. To intercept as many gamma rays as possible, the detector is moved close to the target. So we get alpha particle signals and gamma ray signals. But only signals which come together as a pair are significant. The alpha particle signal tells us when we have observed a nuclear excitation, and the subsequent gamma ray signal records the resulting de-excitation. Much of this electronics, including the computer, enables us to identify those relevant gamma rays. And now we're ready to start the experiment.
Okay, ready to start the drive motor now.
Several million volts are now building up inside the Van de Graaff accelerator. Into this end of the accelerator, we must now introduce the particle beam. Alpha particles are, of course, the nuclei of helium atoms stripped of both electrons. So, we start with helium gas, and it is slowly leaked into a special chamber, where helium atoms are made into electrically charged ions. The gas flow can now be monitored as an electrical current.
Okay. Let the beam through.
With the right current level established, the next step is to filter out any unwanted impurity ions using a magnet, just as in a mass spectrometer. A pure stream of helium ions emerges and is passed into the accelerator, where the ions are rapidly accelerated by the high voltage to emerge at the far end as alpha particles with very high velocity. Fine adjustments are made to narrow the beam right down until it's only a millimeter across. This magnet bends the beam through 90 degrees and ensures that the alpha particles, which travel down the beamline into the experimental hall, are all tuned to nearly the same energy. For this experiment, the alpha particle energy is around 17.06 million electron volts. So, with the particle beam on, the beam colliding with the target, the detectors in operation, data builds up.
Well, the experiment has now been running for some time, and what we've just seen on the display screen here is a build-up of some of the data that's now stored in the computer after some hours. So let's have a look to see exactly what we've got. Well, along this direction, energy is increasing, and in this direction, we've got the number of particles at a particular energy. This, in fact, is the energy spectrum of the alpha particles, and we've expanded the scale so that the zero is way off there to the left. Now, what about this very highest peak of all, this highest energy peak? Well, this corresponds to alpha particles that didn't transfer any energy to the interior of the magnesium-26 nucleus. This next peak shows the least amount of energy that was transferred by the alpha particles to the nucleus. And these alpha particles raised the nucleus from the lowest energy level to the first level above that level. And this interval, well, that's proportional to the energy difference between the first level above the lowest and the lowest. But it's very difficult to get an accurate value from this kind of plot of that energy difference. So what we want to do is to get rid of that alpha particle spectrum and have a look at the gamma rays that are just associated with that particular peak of alpha particles. So you see we've just got one line. All the alpha particles in this case gave rise to this particular gamma ray. And this gamma ray corresponds to the nucleus returning from the first level back down to the lowest energy level again. And from this plot, we can get the energy accurately. So that gives us just one level. And in fact, it turns out that the energy level that we've been looking at is 1.809 MeV above the lowest energy level of the magnesium-26 nucleus. Well, how do we get the other energy levels within the nucleus? Well, to see that, we must now go back to the original alpha particle spectrum. We've looked at this peak. We now want to look at this one. This corresponds to rather more energy being transferred by the alpha particles to the nucleus. And in fact, these alpha particles raise the nucleus from the lowest energy level to the second level above that. So let's have a look at the gamma rays that are associated with that particular peak. As you can see, there are 3 lines. But the nucleus goes back to the lowest energy level in just 2 ways. This highest energy peak is one way, and it represents a transition from the second energy level above the lowest straight back to the lowest level. And it gives an energy of 2.939 MeV. The second way by which the nucleus can return to the lowest energy level is given by these 2 peaks. This peak represents a transition from the second to the first, and this peak from the first to the lowest energy level. But the real interest in this experiment was in much higher energy levels of the nucleus. So let's have a look at the gamma ray spectrum now corresponding to alpha particles which gave up most of their energy to the nucleus. As you can see, there are lots of lines. There are now very many ways for the protons and neutrons to make transitions from this very high energy level back down to the lowest energy level. But of course it doesn't stop there. The team then get together and discuss the results in full detail, analyzing them as carefully as possible and making sure that all the results are reliable. And then the ultimate goal is to publish a paper in a scientific journal where other scientists can read and improve their understanding of the magnesium-26 nucleus based on the work of this team at Liverpool. So, in this program, we've seen how our basic understanding about standing waves on a string led us to consider the standing probability waves that describe particles in the atom. And not only have we improved our understanding of the way that the electrons move around the nucleus, but of the very nucleus itself.